Welcome to Control 4 Driver Development Essentials. My name is Peter Cosenza. This video is the first module in the 400 level training series. This series of videos will build upon the information that we covered in the 200 and 300 level series. If you haven't had an opportunity to view those modules, now is a good time to do so. Going forward, we'll be covering information that assumes a level of familiarity with the Control 4 architecture and device driver fundamentals that is provided in these preceding training videos. In this video, we'll look at a device driver from a structural standpoint by breaking it down into manageable blocks of code. You'll find that each of these blocks serve a specific purpose and also work together, providing control to your device. By the end of this video, you should have a good understanding of each of the components that make up a device driver and hopefully be thinking of ways you can leverage them in your own driver development efforts. We have a lot of code to review, so let's get started. For the purposes of this video, we're going to use an XML editor to display our driver content. There are several XML editors available for free download. Here, we'll be using First Object. It is available for download at www.firstobject.com. A good XML editor is useful in that it can take a lengthy, complex driver and present it in a way that's much easier to review. We'll be reviewing the code found in a receiver driver in this video. This particular driver has over 2,000 lines of code. When each of the sections of the driver are collapsed in our XML editor, it looks like this. The first line you'll notice in our collapsed driver is the device data tag. All driver code resides within the device data tags. You can see in our example that device data is the first line of code as well as the last. Device data is a root element and it is required to be used in this manner. The beginning of our driver code contains a fair amount of high-level information about our driver. As we've discussed in previous modules, this information is important and, in most cases, must be included. The tags that contain text data are named rather intuitively. Tags such as name, model, and copyright are pretty self-explanatory. However, there are a few that we should discuss for clarification purposes. The small and large tags are used to include icons for your device that will be displayed in Composer Pro. These do not impact how your device is displayed in Navigator. The control tag is used to designate if the driver was created using DriverWorks and Lua. A case-sensitive value of DriverWorks must be entered here. Now that we've spent some time reviewing the overview data that your driver should include, let's dig in deeper and take a look at the code that makes up the majority of our receiver driver. The first section of code that we'll review is the contents contained in the proxies tag. Many devices require the use of only a single proxy. Light devices, TVs, and DVD players are examples of devices that require only one proxy for their driver to control a device. When using a single proxy, your driver can specify the proxy using a simple declaration in the C4I file. For example, proxy, DVD, and proxy, or proxy, TV, and proxy. We've chosen a receiver driver for this training module because it uses several proxies. In fact, if we open up the proxies section of our XML, we can see that this particular driver uses 10 proxies. You'll notice that a receiver proxy and a tuner proxy are declared. The rest are media player proxies. The media player proxy is used as a default proxy to support components of our receiver that fall outside the defined Control 4 proxy list. Control4 offers a receiver proxy as well as a tuner proxy, and both of these are obvious candidates for inclusion within our driver. However, this particular receiver has a rich feature set. It provides internet radio, has a media server, Pandora support, and other features. And Control4 does not offer a proxy for those particular services. The media player proxy is used as a generic proxy to provide control for these features. If we open up one of the proxy entries in our XML editor, we can see that each is comprised of two components: the proxy binding ID and the proxy name. A proxy binding ID is a numerical value that is assigned to each proxy used within a driver. It defines an identification binding value that represents a relationship between a proxy and the driver. This ID value is used often when sending data and ensures that the correct proxy data relationship is always established. Control4 drivers support a range of binding ID values. These ranges are predefined based on the type of control being declared in the driver. For example, there are binding ID values for network bindings, power management, and room bindings. Since we are binding a proxy, we'll need to use an ID value that falls in the range between 5,000 and 5,999. If we take a look at the XML for all of our defined proxies, we'll see 10 entries. Let's look at them in the actual driver code. The schema is defined within an open proxies tag and a closed proxies tag. Notice that proxies is plural, since this tag may contain one or many entries. Each entry begins with an open proxy and ends with a closed proxy tag. The format is the proxy binding ID, in quotes, followed by the proxy name and the Control4 proxy being used. Note that the format used in our example must be followed. Notice that proxy is singular since only one proxy can be declared in this tag. The next section of our driver defines all of the capabilities supported by our receiver. Capabilities are defined in a proxy and referenced in protocol drivers. They represent typical functionality and physical characteristics found in devices of a given device class. Values for each capability are entered in a protocol driver and then in turn exposed to the proxy. This enables the proxy driver to determine what capabilities are supported by the device defined in the protocol. Now, let's take a look at the capabilities for our receiver. If we take a look at these capabilities, you'll notice that many have a value of true or false. However, some capabilities require a numeric value. For example, the tuner in our receiver can support up to 63 preset channels. That's defined in the preset count capability. Now, let's take a look at the capabilities section of our driver code. Much like the code structure used in the proxies section, the capabilities are defined within an open capabilities tag and a closed capabilities tag. You'll notice that the formatting for capabilities is rather straightforward. The capability is provided in an open format, followed by the capabilities value. Finally, the capability statement is ended with the name in a closed format. You've probably already noticed that this receiver supports quite a few surround modes. Surround modes are considered capabilities and reside within the capabilities code block. They are defined by the device protocol and have an ID value and a name when modeled in the driver. The next significant part of our device driver is the connections section. Connections are the bindings defined in a driver and used within the Control4 system. Generally speaking, they are visible through Composer, In the case of AV, control, and room bindings, they are reported to the proxy driver when they are bound together in a project. To understand connections better, it definitely helps to examine one and understand its elements. Let's go back into our driver code and do just that. We'll start with our first connection, which is the serial control connection for the receiver. If we expand the connection itself, we can see all of its elements. The ID is the identification value of the connection. In the case of this serial connection, the value is 1. The range of valid control connection IDs is 1 through 999. The connection name entry indicates the name of this connection. This name is used by Composer to display the binding. The type value represents the type of connection we are defining. Supported connection types include control, proxy, audio-video, network, video, audio, and room. Since our connection is a serial connection used to control the actual receiver, we'll pass the type of 1 for this connection, since 1 is the predefined value that correlates to the control type. Consumer provides the ability to define if this device connection is an AV consumer. For example, if the device has an audio or video input, it should be designated as a consumer. A value of true indicates that the connection is a consumer. Finally, we need to discuss the class element of a connection. Each connection defined in the driver requires a connection class. Also, some connection types support multiple class entries. Connection class information is defined inside each connection instance within the connections code block of a driver. A connection class indicates the physical data or signal type that a specific connection can transmit. For example, the class information of our connection is RS-232, and its class name is RS-232. Let's look at another connection, and we'll see how this value and others will vary depending on the device's physical connection, as well as the data that needs to be delivered. Let's open up the connection that's been created for the tuner portion of our receiver driver. Here, we see the use of our proxy binding ID that we discussed earlier. And you'll also notice the use of the hidden tag. When hidden is added to a connection and set to true, the connection will not be visible in Composer or to the end user. This enables us to define permanent bindings that we do not want altered by the system programmer. For example, our tuner needs an audio connection bound between the tuner proxy and the receiver proxy. This establishes the valid AV path that is needed by Director. You'll also notice that we have quite a few more connections defined in this driver. If we open up the class XML for the favorites connection, you will see the use of AutoBind. AutoBind marks this class as needed to be auto-bound. If an AutoBind ID is provided, which in our case it has, then this class will be connected on that binding. Otherwise, it will be connected on the first connection in the project providing this class. Let's look at one more connection before we move on. Here is the connection for Pandora. Again, we see our proxy binding ID value being used. Also, take a look at the ID value. It is 1033. That falls in the range for video inputs. Our connection is hidden, and here again we see several classes defined using the AutoBind tag. They will bind automatically to a video output connection with the ID AutoBind value of 13. The last code area we'll review in this driver is the config section. The config area of a protocol driver contains all of the device-specific configuration properties. The Lua code is also incorporated into the config section. The config section of our receiver driver contains a lot of schema, including the script section, which defines all of the Lua functions and commands that our driver will use to implement device control. It is defined by an open config tag and ends with a closed config tag. But before we get that far, our driver has some other important declarations contained in its config area. The first thing we see under config is the power management method tag. It is important that our driver passes the always on value in this tag. The next section is the IR section. The IR section contains all of the IR codes that are used to control our receiver. The properties of each IR code reside within an open IR code tag and a closed IR code tag. For example, let's take a look at the IR code schema for the DVD IR command. Here, we can see the IR code's ID value, its name, transmit type, repeat count, and delay information. That's followed by the actual code and any alternate code patterns, if applicable. We can also see the same information in Driver Editor under the IR Codes tab. This is followed by our serial control settings. Again, these can be seen in Driver Editor as well. Documentation is followed by the script code section. If we look at the script tag and our driver code, you will see that it is followed by the C data tag. All of your custom programming using the Lua scripting language is inserted between the C data tag and the double close bracket. The contents of the script area of our driver warrant a training module all on its own. We will examine the contents of this area in 401 Module 3, a look at the protocol driver. The actions area of our driver provides the ability to include some programming that might be useful during driver installation. Actions are similar to device-specific commands. However, they are primarily intended to be used during driver installation and configuration. They can only be activated on the Actions tab in Composer and are not available for programming within the system. In our driver, only one action is defined: destroy all timers. In our code, we can see that it is defined by its name and a command name. We can also see this action and execute it in Composer Pro. Next, we have the commands section. The commands defined in this section of the driver define functionality that falls outside of the commands provided by the Control4 proxy. In our case, the receiver proxy has no commands to configure the HDMI outputs. In order to provide control for this, we've defined commands to handle it here. The last significant section of code that I'd like to discuss is the properties area. DriverWorks properties, as defined in the C4I file, are exposed in the Composer System Design interface on the Properties tab. Properties are data values which are used within your driver. These are initialized in the driver code and also may be configured through the Composer Properties page for your driver. Property data types include list, floating point, integer, string, and Boolean. All properties can have initial default values and may be changed by the installer or configured as read-only. Properties persist automatically, so it is not necessary to manually persist them. Let's take a look at a few properties to better understand their requirements. Here is the standard debug mode property. It's used in many drivers. As you can see by the objects within it, it is a list type property. It can be turned on or off because the read-only setting is set to false. The debug property defaults to off, and it contains 4 items, which are types of debug that make up the list, from which a user can choose off, print, log, and print and log. Now, let's take a look at a ranged integer type of property. The power on delay uses the ranged integer type to provide a default power on time of 10 seconds. The value can be adjusted by the installer using values between the minimum of 6 and maximum of 25 seconds to account for actual device performance. All of the properties defined here can be seen and configured in Composer Pro. We've covered a lot of information in this module, and initially, it probably seems like a device driver is quite complex. We recommend that you revisit this video and focus on one section at a time during your own driver development efforts. The next 2 videos in the 400 level driver development training series will focus on the proxy driver and the protocol driver. After watching those 2 videos, in addition to this one, you'll have gained a solid foundation of knowledge surrounding Control4 device drivers, their elements, and how they fit into the Control4 ecosystem.